Welcome back to the deep dive. So you rely on these incredibly sophisticated AI systems pretty much every day, whether you realize it or not.
So absolutely, for everything from complex research synthesis to, drafting policy.
Yeah, exactly. And we trust them. We trust them because they're fast, they're comprehensive, and honestly, they sound so intelligent, so fluent. But what if that fluency, that confidence, is actually hiding a really deep structural problem? What if the knowledge is, well, what if it's decaying the deeper the AI goes? Okay, let's unpack this. We are diving into a huge new finding called synaptic drift. And it basically suggests that this kind of information decay isn't a bug, it's a law.
It's a fundamental law. This is a really foundational work from the ASEAN Research Initiative led by Ericsson Tajum Katz. And they weren't trying to just benchmark models.
Right, not another leaderboard.
No, they wanted to understand what they called the thermodynamics of knowledge. And the core finding is that when information is recursively transformed...
Meaning the AI uses its own output as the next input. It's basically talking to itself.
Precisely. When that happens, the integrity, the actual meaning of the original source, it starts to erode exponentially.
Wow.
It's an inherent decay process. And it happens even when the system is performing perfectly, generating what looks like flawless text. It's why they use that epigraph. Language does not collapse when it changes. It collapses when change loses its anchor.
That really gets to the heart of it. So our mission here isn't to be afraid of AI, but to figure out how to engineer the continuity of meaning. We have to understand the physics of how these systems fail.
Okay, so let's get into the mechanics of this. They found this structural conflict, and to explain the drift, they had to define two opposing forces, two measurable properties. What are they?
This is the critical insight. They split the output into two key properties. The first is semantic integrity. They call it omega.
Omega, okay.
Think of this as simply truth. It's how well the output preserves the raw meaning from the original source, from what they call $.
So does it align with the facts? Exactly. And the second property is pragmatic coherence, which they label pi. This is all about fluency. How well formed is it? How persuasive does it sound?
So that's fluency. And it's totally independent of whether it's true.
Completely independent, and that's the danger, right? We are all biased toward high fluency. If something is well written, we just naturally trust it more.
Of course.
And this is where their synaptic drift law comes in. What's fascinating here is that semantic integrity, the truth, it decreases multiplicatively.
Multiplicatively.
So exponentially.
Exponentially, at every single cycle. At the same time, pragmatic coherence, the fluency, either stays the same or actually increases.
It gets better.
It gets better because the AI is constantly optimizing for sounding good, for being grammatically perfect.
I have to stop you on that word, multiplicatively. This isn't just a simple game of telephone where one detail gets lost. You're saying this is like a law of informational physics. That's the discovery. It's not about an error, it's about entropy. When an AI summarizes something, it has to throw away specific details to be brief. That loss of specificity is irreversible.
You can't get it back.
You can't. And when it takes that slightly less specific summary and summarizes it again, it's building on an already eroded foundation. The decay accelerates.
It's literally eating its own foundation.
It is. The decay function they came up with, omega times 1 lambda, that n is an exponent, is what's so terrifying. It means the system gets exponentially better at being confidently wrong.
So let's talk about that lambda, the drift constant. You said it depends on the type of transformation. Which operations are the riskiest?
Right. So lambda is the speed of the decay. And they found the highest risk came from highly abstractive operations.
Like summarization?
Summarization was pretty bad, yeah. It had a lambda of around 0.18, so you lose about 18% of the meaning on the first pass, then 18% of what's left on the next. But the worst, the absolute highest risk operation was recontextualization.
Recontextualization. So that's like framing the information, putting a spin on it for a different audience.
Exactly that. Taking a technical report and turning it into key takeaways for leadership. That had a lambda of 0.25 or even higher. The second you ask an AI to interpret, not just condense, you put the decay of truth into overdrive.
Okay, so if we accept this, we have a massive measurement problem. How do you possibly police something that sounds perfect but is, fundamentally broken? Reading for style clearly doesn't work. That's just checking the fluency.
This is where their methodology is so brilliant. They created something called the Objective Canonical Anchoring Test, or OCAT.
OCAT.
You can think of it as a polygraph for AI-generated knowledge. It's designed specifically to stop us from getting fooled by that surface-level polish.
So what does it do? How does it work?
It doesn't try to judge quality in a subjective way. Instead, OCAT fixes what it calls a canonical anchor, an $8. This is the stake in the ground. It's the set of verifiable, measurable facts from the original source.
Got it. The ground truth.
The ground truth. Then the decay of integrity of omega is measured only against that fixed reference point.
So how do you actually measure the truth? How did they quantify that omega score?
They used a composite of 4 things. First, semantic vector alignment to see if the core concepts were drifting. Second, logical relationship retention. Did A causes B suddenly become B causes A? Third, terminological consistency. Are the technical terms staying the same? And fourth, quantitative fact stability. Are the numbers changing? Omega is the aggregate score of how well all of that holds up.
And they applied this test across some really high-stakes material.
They did. Over 2,800 transformations across 100 different sources. And this wasn't blog posts. This was peer-reviewed science, government statistics, medical guidelines, complex engineering docs.
The kind of stuff where if it drifts, the consequences are very real.
Very real.
And the results, the data chart they have is just devastating. It's the perfect picture of this failure.
It is.
Semantic integrity, omega, it starts at a perfect 1.00. After just 5 recursive cycles, it plummets to 0.30.
Just 30% of the original truth is left.
In 5 steps. Meanwhile, pragmatic coherence, the fluency, it actually went up from 0.71 to 0.89.
And that divergence is the whole story. The system creates this compounding chasm between how good it looks and how right it is. By cycle 5, you have an AI producing text that is almost 90% fluent and authoritative.
Only 30% true.
It has become supremely confident in its own fabricated reality.
Okay, but this is where it gets, really unsettling. They didn't just find a gradual decay. They found a specific tipping point. A point of no return.
That's right, a critical phase transition. They found it happened consistently at cycle 3, specifically around 3.2 cycles, which they call C303-ness.
C3?
C is the moment when the lines cross. It's the exact point where fluency pi definitively overtakes integrity omega.
So what does that mean practically? At C3, what's happening?
At C, integrity has dropped below 50%. So you're literally flipping a coin on whether what you're reading is true. But at the same time, the system's fluency is soaring above 85%.
Wow. So you're reading this beautifully written, totally plausible report that is statistically more likely to be wrong than right.
And you would never know. And that's when you enter what they call the vaporwork zone.
Vaporwork zone. I like that.
It's a perfect term. It's the undetected semantic failure zone. Once you're in it, the outputs are confident, they're persuasive, but they are no longer traceably anchored to any source. Fluency has become a mask, not a signal of reliability.
I can easily picture this. A business summarizes competitor reports, that's cycle 1. Then it reframes that for the board, cycle 2. Then it drafts a strategy from that briefing. Yeah. There's 3 cycles right there.
You're already there. You're past $333. And they found that for complex technical content, it was even faster. Technical documents hit $333 at just 2.9 cycles.
Why them? Why do high-risk technical docs drift faster?
Because their meaning depends on extreme specificity. In an engineering spec, if you lose one single variable, one tolerance level, you haven't lost a detail. You may have lost the entire meaning. The utility just collapses instantly.
Right. The cost of that one bit of information is huge. So once you're past C3, can you fix it? Can you just re-inject the source material?
The recovery data is sobering. If you intervene early, at CC1 or 2, you can get most of the meaning back. But by the time you're at C44 or C5, recovery is minimal. Sometimes negligible.
It's gone.
It's gone. The path back to the source has been obliterated by the compounding loss. And if we connect this to the bigger picture, it means that managing this isn't just about quality control anymore. It's about cost prevention. You have to stop the drift before it becomes irreversible.
So if the old tools like compliance checks only measure that deceptive fluency, organizations need a whole new playbook. What's the infrastructure they're calling for?
The mandate is for something they call Enterprise Semantic Integrity, or ESI. And it's a mindset shift. ESI treats knowledge not as a static file, but as a depreciating asset that needs active governance.
So it's not about checking the final product, it's about managing the whole pipeline.
Exactly. And the mandates are very specific. First, transformation depth governance. For critical knowledge, autonomous systems have to be capped, no more than 3 cycles. N must be less than or equal to 3.
A hard stop.
A hard stop. Second, continuous canonical anchoring, using OCAT to constantly measure integrity against the source. And third, mandatory human intervention at $333. Someone has to re-anchor the system before it goes off the rails.
It sounds like it all boils down to accepting that just making the output sound better doesn't save the meaning.
It just masks the decay. Which brings us to the human element. The study totally reframes why you need a human in the loop.
It's not just to catch typos.
No, it's because the human is the reference point. The human holds the tacit knowledge, the original meaning. The human is the anchor. In this research, human in the loop is an infrastructure mandate, not just an optional skill. ESI recognizes that what they call tacit referential custodianship is the only thing that can counteract the drift.
So it's a structural requirement.
It's a structural requirement, which they even formalize as PEJs. The probability of human presence has to be greater than 0 for the system to be stable. The conclusion is just so clear. Autonomy is only safe when it's paired with stewardship. Otherwise, it becomes an exponential liability.
So what does this all mean for you? The takeaway is that synaptic drift isn't a bug in the code. It's a law of informational thermodynamics. Semantic loss is the default path for any unanchored recursive system.
And that means our focus has to shift from correction to prevention. The failure isn't that AI isn't intelligent enough. The failure is deploying that intelligence without the infrastructure like ESI and OCAT to govern the continuity of meaning.
If you don't anchor it, it's going to drift. And once it hits that vaporworks zone, it's probably not coming back. Yeah. Now, we've spent this entire deep dive on text-based systems, mostly in English, where that average decay constant lambda was about 0.23.
And that brings us to the final, really provocative thought the researchers leave us with. If standard text pipelines decay that fast, what happens next?
What do you mean?
I mean, how much higher will that decay constant be in future systems? Systems that blend and abstract not just text, but images, speech, and data all at once.
Multimodal systems.
Multimodal systems. Okay. Or what happens when these systems are operating in languages that are structurally more complex, like agglutinative or polysynthetic languages? The problem we've just defined might not just persist, it could get a whole lot worse, a whole lot faster, which means we really needed to solve this yesterday.